Math 408, L functions and sphere packing. So this is the last of a set of 2 lectures on a little bit of a diversion, on trying to determine if a data set is natural, reasonable, what do you expect in certain things. And the standard probability problem is flipping a fair coin n times. You expect roughly n over 2 heads. What do you expect for the longest run of heads? And I emailed you an absolutely brilliant paper by Schilling where he goes through and analyzes it, and you see that it grows proportional to the log of n. There's a nice double exponential, and the variance is actually bounded independent of n, which means it's incredibly tight. It's very strange. It's very rare to see something like that. And so what we're going to do today is we're going to look at runs. So we will study runs. So if I give you head, head, tail, 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 head, 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 tail, head, how many runs does this have? 5. So this is a run of length 2, length 3, length 3, length 1, length 1. There's a lot of calculations you can do without too much trouble. As you're putting coin tosses down, what is the probability that it continues a run versus starts a new run? It's 50-50. Always?
Yeah, very close.
Always? For every toss?
Not the first one.
Not the first one. Okay, good. So the first toss will always start a run, no matter what it is. But after that, each one is going to be a 50-50. So how many runs do you expect to have if you toss it n times, approximately?
1 plus 2 n minus 1.
Times 0.25?
Isn't it p times 1 minus p?
P times 1 minus p is for variance. Let's say there's n tosses. The variance is the square root of p1 minus p. I'm sorry, the variance is p1 minus p. Standard deviation is square root of p1 minus p if you're doing a Bernoulli random variable. But the expected number of runs with n tosses, well, it's just 1 from the first toss, and then we have n minus 1 tosses. Each toss gives you a new run with probability 1/2. So just be n minus 1 over 2.
2 times 1/4.
And so if we multiply this by, so it would be 2n minus 2 over 4. You had 2n minus 1 over 4.
Oh, then I said that wrong now.
Oh, then that's fine, then you're correct. And you could look at this as it's the expected value of x1 plus xn, where each of the x's are binary random variables telling you, have I started a new run? If you change it so that instead of having just heads and tails, you had more things, it's not a big deal. You just want to know what is the probability it's different than the previous. So what's nice is we already have a smell test answer of how many runs we expect. The question is, how do we compute the distribution? And so we talked about matching polynomials, or matching coefficients. And the other one was differentiating identities. And I will just show one of the most painful calculations I think you can imagine. So let's look at 1 plus x to the n. This is just 1 minus x to the n plus 1 over 1 minus x. If I apply x d by dx, this just becomes the sum, k goes from 0 to n, of k x to the k, and that's just x d by dx of 1 minus x to the n plus 1 over 1 minus x.
I did this problem. I was working on this in the last class.
Oh, were you?
I couldn't. I got messed up somewhere.
This sounds weird from k plus 1.
No.
Oh, no, it's 0, yeah.
So I am allowed to do it from 0. It's going to be fine. What might be an interesting value of x to take for this?
2.
Nope.
1.
1. Because then you get the sum of the first k powers. if I apply it again, I get the sum, k goes from 0 to n, of k squared, x to the k, is x d by dx of x d by dx of 1 minus x to the n plus 1 over 1 minus x. What is the problem with taking x equals 1?
You have 1 over 0.
You have 1 over 0, and that is supposed to bother us in the math department.
Or 0.
Right? So how can we get around this? Well, what we could do is we could take the limit as x goes to 1. Do you want to do it from above or below?
Below.
Does it matter?
No.
No, it doesn't matter.
Yeah.
And in fact, when you say take the limit as x goes to 1, that means x is never 1. So we could calculate this. We can take the derivative, multiply by x, take the derivative, multiply by x. We could also do this one. So if we do this one, you'll have a 1 minus x squared. You'll multiply by x. And we take the derivative of the top, which is going to be negative n plus 1 x to the n 1 minus x, minus this, which is 1 minus x to the n plus 1 times the derivative of 1 minus x, which is, I think, negative 1. Have I done this correctly?
Looks good.
And as x goes to 1, we can see clearly we're going to have 0 over 0. And we can expand this out. How would you handle this? L'Hopital. So this isn't too bad to do by L'Hopital. How many times are we going to have to apply L'Hopital? Twice. Now you'll have a 1 minus x squared below. You'll square that, so you'll have a 1 minus x to the 4th power. It's doable. But here's a way to get the formula for the sum of the kth powers without using induction. No induction. You don't need to know what the formula is. Unfortunately, I don't think it becomes practical as you go further and further down. But it's a nice observation that you can get these formulas in terms of applications of this. So if anybody can find a way to make this nice, this has been something I've had on the back burner for 1 to 2 decades now. And it would be nice to see, is there a way to clean this up? I did a tremendous amount of work, and I was able to get the sums of the squares.
It's really that long?
Yeah. Well, you've got to do 4 L'Hopitals.
You already know this.
But I don't have to use induction. So it is nice that you can solve this without using induction. As you go further and further down, it's going to become worse and worse. And so the question is there a good way to handle them all simultaneously and not just put yourself in a situation where you are just doing ad hoc, painful calculations? But you can use Mathematica to expand this out. You can take derivatives. It's not a big deal. And so it's a very mechanical process that will work. All right, so now imagine we have n1 h's and n2 tails. And we want to know how many runs can we have. And so I'm trying to set myself, as we talked about last time, about a general situation. And later, you might say we have n is equal to maybe n1 plus n2 with the probability of a head equaling p and the probability of a tail in a shaka 1 minus p. And so we want to calculate, if I tell you how many heads and tails, how many runs do we expect to have? How many of you are looking forward to a lecture where we fill blackboard after blackboard after blackboard with technical, long, tedious calculations? Good. So what I'm going to do is just give you a high-level approach of how you would do the calculations, and I actually have written up this. I have not lectured on this material since probably around 2008, when I was teaching mathematical statistics at Brown. And it was a lot of fun teaching that class. So how can we handle this? Well, I'm going to just state what the result is, and then we only prove the special case. So let's let u equal the number of runs in the above. And then we assume all n1 plus n2 choose n1 arrangements are equally likely. And then if u equals 2k, this happens, this is just poorly written in my notes. I will have to yell at old Steve. 2 n1 minus 1 choose k minus 1, n2 minus 1 choose k minus 1. Okay. And then I think in the calculation, I think I choose n1 to be the larger of the two numbers. And so, also there exists an equation if u is 2k plus 1. But for simplicity, let's just look at the case when we have an even number of runs. The first thing is we want to get a sense of how reasonable an answer is. And so there's a couple of ways to do this. A lot of times it's useful to look at extreme cases. So what might be extreme cases? Okay, good. So if n2 equals 1, so if we have an even number of runs and n2 is 1, what does that mean? It's either the first or the last. Without loss of generality, we can assume we start with a head and end with a tail. And the 2 will take care of that, because if we go head to tail, if we flip all the heads to tails, so not heads to tails, if we turn the string backwards, then we go from tail to head. And they can't be the same string because one starts with a head, one starts with a tail. So without loss of generality, it's head, something, tail. And that gives us the factor of 2. How many heads do we have left?
n1 minus 2?
Nope.
n1 minus
n1 minus 1 heads, and how many tails?
0.
So n2 minus 1 tails in general, and in this case we would have none. So there would be absolutely no freedom. So in this special case when when n2 equals 1, we know what to do. What if n1 is enormously larger than n2?
That doesn't seem.
You want really like 2 n2 runs?
Yeah.
Yeah, so then you would expect,
Like n2 runs.
so how many runs?
Around n2.
2 n2 because you have
2 n2 because each n2 is 2 n2.
So each n2 gives you 2 runs. So expect maybe 2 n2 runs. And so that would be taking k equals n2. And does that seem reasonable? We know, let's assume n2 is less than or equal to n1. So we know k, what do we know about k relative to n2?
K is roughly equivalent to? Or no, K is roughly...
So in this particular situation, k would be n2, but in general, what can you tell me about k and n2? Or 2k and n2? So is it bounded by 2 and 2, or? So I think this should be less than or equal to maybe 2 minimum of n1 and n2. Because the best you can do in terms of getting as many runs as possible is to assume that whichever one is smaller, you never have them align. And that will give you as many changes.
We just assumed n2 is
Right.
small.
Yes. So I am going back and forth between doing things in a special case and just writing things in general. And we can cancel the 2's. So we know k is at most n2 in our situation. So we have k is less than or equal to n2. So when you look at this, this is going to become largest when k is as large as possible, because then we're going to get a higher polynomial of n1 minus 1. And so most of the runs will come from, the largest term will come from k equals n2. Because this term is itty-bitty. N1 is so much larger than n2, the contribution from this is meaningless. It's dwarfed. So I want to make this term as large as possible. So I expect the maximum is going to be when k equals n2, when n1 is much, much larger than n2. And we would get n1 minus 1 choose n2 minus 1 possibilities. And if you think about that, you have your string, and you're basically choosing where to put the tails. So if we have our string of heads, here's the initial head, here is the final tail, and then after each head, we have a possibility to place a tail. We're never going to put two tails together because that will be lower order. That's not going to give us as many runs. We expect when n1 is so much larger than n2 that everything is going to be runs of tails of length 1. It's just so improbable we'll get two of them next to each other. So how many spots do we have? We have n1 minus 1 spots. And we choose k minus 1 choices, because the last one is fixed on us, and that's just also n2 minus 1. And that's where this is going to come from. So again, whenever you can do a smell test to get a sense of is your answer reasonable, I strongly encourage you to do this. Looking at extreme cases, the formula seems plausible. So now we want to prove this formula in general. If we can do it for the evens, we can do it for the odds. It's just a little bit more work. But what I really like about this problem is just trying to get a sense of what the answer should be before you do all the calculations. Okay. So we have a formula. 2 students in the class should be thinking of a certain problem right now. Or maybe 3, because we have some people who took probability with me, as well as did research. What problem should you be thinking of? Yes, the cookie problem or the stars and bars problem. We have partitions, and we're trying to choose where to put our items. So consider.
Cookie problem or the star?
I'm sorry?
What are either of those?
So we'll see a variant of it. to the cookie problem.
What's the matrix problem?
So you have C identical cookies, and you have P distinct grad students. In engineering, it's not clear that these are considered distinct because the professors don't always know the difference, but we'll assume they're distinct. And you want to divide the cookies among the grad students. How many ways can you do this? And the answer is C plus P minus 1, choose P minus 1. And so, for example, if C equals 8 and P equals 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, which is 8 plus 4. And now Cookie Monster comes and he eats 4 cookies. He eats P minus 1. This is the classic Cookie Monster. It's what Cookie Monster does. Leave him alone. For extra credit, what was the original color of Oscar the Grouch on Sesame Street?
Blue.
No.
Red.
Orange.
Orange. Oh.
So notice what happens. When I eat 4 cookies from 14, the remaining 8 cookies are partitioned 3, 0, 2, 2, 2. There's a one-to-one correspondence between the number of ways I can eat 4 cookies from 14 and the ways I can assign cookies to 5 people.
But in this scenario, one tree is getting kind of screwed over.
Yes. And so what we're really doing is we're solving this Diophantine problem in the integers. And we want each xi to be an integer at least 0. Now, it bothered you that one of the students was screwed? Grad school is not for you then.
That student.
You accept this. I think the best way to describe graduate school was we had, social hour at Princeton once a week. We had, a happy hour. So you knew for 1 hour each week, this was your time to be happy. So you don't like the fact that student 2 was screwed, right?
Maybe they deserve it.
Well, let's hold the boat. Let's write xi as yi plus ci. And what we're going to do is we'll assume each person I has to get ci cookies. So now x1 plus xn equals c. Well, that's the same as y1 plus yn equals c minus c1 plus cn. And now we're just distributing the excess cookies.
So you could give one cookie to each student and figure how to do it.
Right. Is each student starts with 1 cookie, or maybe the seniors start off with 2 cookies, the juniors with 1 cookie, and the freshmen and the sophomores, we screw them. As an aside, imagine I want to sum little c goes from 0 to big C of c plus p minus 1 choose p minus 1. So the way you can interpret this is I have big C cookies. And you give less equal to C cookies to P people. And so maybe I give no cookies and everybody gets screwed. Maybe I give 1 cookie, 2 cookies, all the way up to C cookies. Can anybody see how to quickly evaluate that sum?
Give Cookie Monster the rest.
So give Cookie Monster the rest. Add Cookie Monster. So if we give little c cookies to P people, that's the same as giving the remaining leftover cookies to Cookie Monster. So this is just big C, because that's how many cookies we have, plus P, choose P, because we now have 1 more person. So if you look at things the right way, a lot of combinatorics falls out immediately. It's hard sometimes to see these relations and to see the story. This is one of my favorite problems. And I've had several students prove beautiful theorems using this. All right. So what we have now is going to be very similar to the cookie problem. So I'll try to keep this stuff over here still on the board and just write down here. So we want to have, so we have n2 less than equal to n1. We start with a head. We end with a tail. And we want 2k less than equal to 2 n2 runs. So we can imagine we have all of our heads. We know we have to put a tail over here. That's forced on us because we want to have an even number of runs. And now we get to decide where do we put the different runs. We could start a run after here of tails, a run after here of tails, a run after here of tails, a run after here of tails. And we have to start a run after here, right? So we might actually have, so we know there's a tail here. There might be some other tails here as well. But we know this is forced on us. So how many places do we have to choose to start our run? We have n minus 1 heads.
Is it 2k minus 1? Or wait, is it where to start the run? Or
Well, we have to choose how many starting points do we have to choose?
n1 minus 2.
Not n1 minus 2. How many runs do we have?
2.
2k runs. So we have 2k runs. The last choice is forced, and that last choice is going to give us. So how many things do we have up until this one which we have to take? We have n minus 1 things here. How many of them do we have to choose?
2k minus 2.
I don't think it's 2k minus 2. I don't think it's k. I think it's k minus 1.
Oh, because each place gives you 2 runs.
Each place gives us 2 runs, and then the one over here is going to give us, because we don't count this as a run until we put the tail after it. And that's what we're trying to get. So that's the first factor, which is over here. Now we have the second factor. Well, we now have our choices where we have our tails. And so we have to split the tails and put them into here. So we have k minus 1 places. And we have n2 minus 1 tails. And I want to make sure I do this properly. We've got to be a little bit careful because we know we have a tail here. So actually, I think we have k places. And we know we have to choose a tail here, but we could choose other things. How many tails do you want to put over here? At least one. So we have, say, T1 plus 1. And T1 will be the excess over the one that we're forced on having. How many will we have here? T2 plus 1. T3 plus 1. And all the way over here, Tk plus 1. And so if we sum the t's, and then we add k, because we add 1 every single time, that has to equal the number of tails we have. Right? So this is the same as T1 plus tk is n2 minus k. That's the cookie problem. How many cookies do we have? So we have n2 minus k cookies. How many people do we have? K. So it's going to be plus k minus 1 people. Choose k minus 1. And that's this factor. The two factors are the same, but the analysis is completely different in terms of how we do this. But if you haven't seen combinatorics like this, a lot of number theory as you go further is just good combinatorics. And this proves the formula. And now I am claiming that if you sum all of that, we want to figure out then how many runs are there. This is how many times we can have a run of length 2k. So what would we have to do? I'm sorry? Do the odds, and then we would have to sum them all together. We might be able to just get the answer without actually doing the summation. If we were in the nice situation where each thing was, say, 50-50, we might be able to make some kind of argument that we know the expected value, and therefore we could figure it out. But we really need to calculate now what's going on with the odds. I'm not going to bother writing down the formula. And now what we want to do is we want to figure out what is this sum equal to. Or related to this, what is the expected value of this sum? And so I think the first thing we want to do is calculate the sum. Okay. So I'm going to calculate the sum of the number of even terms. Yes.
So
Okay,
that
yeah.
comes from, like, if you reverse it, you get the same answer, right?
Why we have the 2 and everything?
Yeah.
Yes, because we're starting with a head and ending with a tail.
Okay, but then but we also have that n1 is greater than equal to n2.
Yes.
So don't you need another factor of 2 for the inverse?
So I don't think we have used the fact that n1 was greater than n2 in this analysis here. So that's a good point.
Okay.
We only used that we made sure that 2k had to be less than equal to the minimum of 2n1, 2n2.
Okay.
But you're right. I never used that in the calculation. I just used that for trying to get a sense of, for definiteness, might as well assume. But you're right. It is very easy to make a small mistake like that and all of a sudden not be considering the most general situation. Okay. So we want to calculate how many evens there are. How many runs of even length are there? So how many even runs? And I just want to make sure I do this in the way I want. All right. So let's look at x1 plus y1, and I want n1 minus 1. x2 plus y2 to the n2 minus 1. And so if I have the x's as different things, I'm not going to be able to. But if I now take x1 equals x2 equals x, y1 equals y2 equals y, it'll be a little bit more convenient to have x1s and y1s and x2s and y2s later when we want to calculate the expected value, because then we can do differentiating identities. We can have the derivative only take down one side. But let's collapse them all. So we get x plus y to the n1 minus 1, x plus y to the n2 minus 1. What will that equal? X plus y to the n1 plus n2 minus 2. And these polynomials have to be the same. So when we expand this out, I just want to try to use the same notation as in the books. Okay, so it's going to be k1 goes from, I think, 0, or it goes from 1. I can do it this way. Right. 1 to n1 minus 1. So I spent a lot of time trying to think of the nicest way to do this. So I'm having k1 range from 1 to n1 minus 1, because now instead of having a k1, I have a k1 minus 1, which is matching with what we have up there. And then this would be x to the k1 minus 1, y to the n1 minus k1, I think plus 1.
Don't you want the upper bound to be n1?
Yes. Yes, you're right. I want it to be n1. And then if I look at this, actually I don't think I want the plus 1, because then this will give me n1 minus 1. And then for the second one, I'll have a sum of k2 goes from 1 to n2, and I think I might want to flip it on this one. Flip it, or do I do it the same way? Oh, I did it the other way in this one. Just to make things match. This one I had as n1 minus k1, sorry, and this one I had as k1 minus 1. And then on this one I had n2 minus 1 choose k2 minus 1, x to the k2, y to the n2 minus k2. And this will be the sum. K goes from, and again, just trying to keep the algebra as nice as possible. I will have go from I'll just leave it like this. So let's put things together. We can have a sum, k1 goes from 1 to n, of n1 minus 1, k1 minus 1. And if we take the special case when k2 equals k1, we would get n2 minus 1, k1 minus 1. Right? And then we would have, if k, this is, you're coming from k1 equals k2, so x to the n1 minus k1, x to the k1, that just becomes x to the n1. And then over here, I would get y to the n2 minus 1. Oh wait, this is probably k2 minus 1 over here, because things were a little bit asymmetric. There we go. And so this is just the coefficient of x to the n1 minus 1, y to the n2 minus 1. Well, how do I get that coefficient over here when I expand this out? So if I want x to the n1 minus 1, y to the n2 minus 1, that's just going to be n1 plus n2 minus 2, choose n1 minus 1. And so we've now shown that this sum and this sum are the same. So we've calculated how many runs there are of even length. And we did this by matching coefficients. We got the sum we wanted. We can multiply by 2. That's not a big deal. Any questions on this? The hardest part here is making the algebra match nicely. And here, this is why I'm just checking my notes to see what's the way to do it as cleanly as possible. Yes?
Wait, is this the number of runs of even length or the number of configurations in which it's holding on?
Sorry, this is the number. This is the number of configurations that have an even length, that have an even number of runs. You're right. Yes. So this is the number of configurations with an even number of runs. And we know this is the number of runs of even length 2k. So if you want to do a conditional probability, what is the probability you have a run of length 2k, given that you have an even number of runs? it would just be that number divided by this number. If we wanted to calculate what is the probability you have a run of a given length, we would also have to calculate, well, how many runs of odd length do we have? Pray to God that it's another binomial coefficient, and maybe you can add them up together nicely. And that will give us the probability of having a run of a given length. And yes?
Can't you just calculate the total number of configurations and subtract the number of each runs different problems?
So the question is, can you get the total number just at a higher level? And so if you think about it, we have n1 heads and 2 tails. So it should be, the total number of configurations should just be n1 plus n2 choose n1. And you can see that this is kind of looking like maybe a component to that. And maybe there's like a Pascal identity or something coming into play. A Pascal identity coming into play.
What's a Pascal identity?
You like Pascal's triangle. The other thing is, I think we also have a fact of 2 that we need to put in here in terms of how many configurations there are. Because the number of configurations was twice that binomial coefficient. So, you know, modulo some of the details. Is the general picture clear as to how you would do this? And, you know, I think you're absolutely right that we can quickly say we know how many configurations there are. Well, if we know that and we know this, we can even figure out how many odd configurations there are. We can figure out the probability that you have a fixed number of, you have a configuration with 2k runs. And now the only thing that's left is the expected value. And so I will show you how to do the expected value calculation. If you wanted to do the standard deviation or the variance calculation, it would be similar, but just a little bit more painful. So this is for the number of runs. So if have an even number of runs, what is the expected value? So it's going to be the expected value of 2k times the probability that we have a run of 2k given that we have an even run. So actually, oh, I'm sorry, not expected value. This would just be the sum. K goes from 0 to the minimum of n1, n2. I can start at 0 because that's just going to give me a 0 there. We know there's no probability of 0. So this is what we need to compute. We know what this probability is. Does the 2 really bother us? No, let's get rid of the 2. And then I'm going to do one of my favorite things. I'm going to write k as k minus 1 plus 1. The reason is the plus 1 is no problem, because when the plus 1 hits the probability, that just sums to 1. Right? So we're using the deep fact k is 1 plus k minus 1. So I can pull a 1 outside and have a k minus 1. Why do you think I want to have a k minus 1? It's erased now, but remember we had the n1 minus 1 choose k minus 1. So it's going to be nicer like that. And so to just try to write things nicely.
Isn't it k plus the sum?
I'm sorry?
Am I crazy? Or not k, shouldn't it be the minimum of n1, 2? Because we added a 1 in our sum. If you're pulling it out everywhere, you need to pull out n1 or n2 sum. N1 or n2.
No, because you're summing the probabilities. It's 1 times the probability. And so when you do 1 times the probability, you will just get the probability. All right, and so now what I want to do is I want to look at x1 plus y1 to the n1 minus 1, x2 plus y2 to the n2 minus 1. And so if I expand this out, and we're running out of time, so we'll just look at the notes. This is going to be a sum k1 equals 1 to n1, n1 minus 1, choose k1 minus 1, x to the n1 minus k1, y to the k1 minus 1, and then we'll have a sum k2 equals 1 to the n2, n2 minus 1, k2 minus 1, x to the k2 minus 1, y, oh sorry, this is x1, y1, x2, y2 to the n2 minus k2. And now we want to get a k1, a k minus 1 coming down. So what do we do? Take d by d, I think, y1 and multiply by y1. And then we'll get n1 minus 1, x1 plus y1 to the n1 minus 2, x2 plus y2 to the n2 minus 1. We'll have a sum k1 equals 1 to n1. We have a k1 minus 1, n1 minus 1, choose k1 minus 1, n2 minus 1, k2 minus 1. We have a sum, k1 goes from 1 to n1, k2 goes from 1 to n2, and then we'll have x1 to the n1 minus k1, y1 to the k1 minus 1, x2 to the k2 minus 1, y2 to the n2 minus k2. And so we want the term when k2 equals k1, right? Take the k2 equals k1 term, and that will give us exactly the sum that we want. And you'll just take the k, when k1 equals k2, you'll have x1 to the n1 minus k1, x2 to the k1 minus 1. At this point, what should we do to the x's? Yeah, at this term, set x1 equals x2 equals x, y1 equals y2 equals y. Then you'll get a specific coefficient on this side. Then you match the coefficients, and then you would take, I believe, x equals y equals 1. Perfect. And once you take x equals y equals 1, then you'll just have this sum. And this sum is essentially the probability. The only difference between that and the probability is we haven't divided it by the correct denominator. So this is the high-level approach as to how you do it. It's clever combinatorics, looking at things the right way, but we are able to calculate the expected number of runs. And so this was doing the even case, then you do the odd case, you put them all together. You can calculate the expected number of runs. You can calculate the variance or the standard deviation. Then you can go one step further and you can say, well, what if we don't start off with n1 heads and n2 tails? What if we have a fair coin? Or more generally, what if we have a biased coin? In all those cases, you can still do the calculation. And then you just keep building it up, building it up, building it up, and I'll send you the notes. But now you will have a great formula for how many alterations do you expect to have between heads and tails. How many runs do you expect to have? And these are just really good tests to see various things about your data. And in particular, when you're looking at the discrete optimization problem, are you seeing strings where the floor beats the ceiling? Or are they essentially like rapid fire alternating between the two? And so I'm really looking forward to seeing what you guys find. I have absolutely no idea. I haven't looked at it yet.
Well, you'll notice something interesting. After 1928,
Yes.
it's all the same. It's all the way ceiling.
That is incorrect.
Incorrect. All right, I'm going to stop here.